This is problem A, Frog 1 from Atcoder Educational DP Contest. The problem states that there are n stones numbered from 1 to n. For each I, the height of the ith stone is h of I. There is a frog who is initially on stone 1. He will repeat the following action some number of times to reach stone n. The action is that if the frog is currently on ith stone, he can jump on to the I plus 1th or I plus 2th stone from I to I plus 1 or I plus 2, and the cost incurred in a particular jump from I to j is the absolute value of the difference between their heights. And we need to find the minimum possible total cost incurred before the frog reaches stone n. Constraints for n and h are as follows: n up to 10 raised to 5 and heights up to 10 raised to 4. Okay, so the first thing that we can observe here is how the transitions between the jumps are happening. Since initially we are at stone 1, let's say n equals to 5 in this case, then we have 5 stones. From the first stone we can jump to the second or the third, because we are only allowed from I to I plus 1 or I plus 2. The cost of this is h1 minus h2, the absolute value of the heights difference, and in this case this is h1 minus h3. This is how the transitions are going to look like if eventually for some intermediate stage we would have these choices. For the fourth stone it has only one choice because the I plus 1 stone goes outside the range, hence that is not possible. So this is how the transitions are going to look like. Next up, if we jump from any I to j, in that case the total cost incurred is hi minus hj according to the question. Okay, so the main idea here is, so we can use a dynamic programming approach where we start jumping from index equals to 1. This is the starting point, starting position of the frog, starting position, and we try all possible jumps that are available from a current index position id. So from id we can move on to id plus 1, and some cost would be involved in that, or we can move on to index id plus 2 and some cost is involved in that, and we add the cost of that jump and move on to the next index that is available. So from id we will move on to id plus 1 or id plus 2, and we try all possible jumps and take their individual costs as well as the cost to arrive or start at a particular index id. Next up, we will try to minimize the solution over all possible choices. So let's try to understand that. Suppose we were at some index I, and we can move to index I plus 1, and the cost in this would be h of I plus 1 minus h of I, or we could have moved to index I plus 2. The cost in this case would be the absolute value of the heights difference. Now, if you look clearly, since we are trying to find out the answer to start, we need to, this blue portion denotes that we need to go from I to N, and essentially if we are going to start at I equals to 1 only, but for an intermediate state where we are for arbitrary state we want to know what are the choices available to us. So these are the two choices that are available, first and second, and this state means that we want to go from I to N in minimum cost. And once we take the first or the second choice, so let's say the first choice is chosen, in that case this range is now, this orange part denotes the answer, means we need to find the best possible answer from I plus 1 to n, and it essentially finds out the minimum cost to go from I plus 1 to n. Or the second choice was to go from I plus 2, and it denotes the minimum cost to go from I plus 2 to n. Notice that this is a overlapping subproblem, which means that each of these individual boxes denote the best possible answer that is available or that can be computed from some starting index, which was I in this case, I plus 1 in this, and I plus 2 in this. So if we want to consider the answer to go from 1 to n, that means we should know what is the index that we are currently at, and that should be included in the state of the recurrence function that we are going to implement. So we must store what is the index of current position. This is the only state we need to store. And one more thing to note here is this blue part, let's say now we know the state of the recurrence, so let's say go of id denotes minimum cost for the travel from index id to n. Okay, now if we understand from this diagram here, the blue part denotes go of I, the orange part denotes go of I plus 1, and the red part denotes go of I plus 2. It is evident from this diagram, and since these are independent and overlapping subproblems, we can deduce the recurrence relation from them. So we started from some index id equals to 0, id equals to 1, starting position of the frog, and let's say go of id denotes the best possible answer or minimum cost to go from id to n. And as we saw from id, we had two choices, id plus 1 with some cost c1 or id plus 2 with some cost c2, where c1 was the absolute value between the heights difference, c2 similar. Okay, now the recurrence relation can be deduced as follows. This the both choices that are available to us, we will find out the minimum among them, and the first choice is to take this index, go to this index, cost incurred would be c1, and the leftover part from that particular would be go of id plus 1. Or the second choice is to go to the next id plus 2 index, and the leftover indices would be from this, which exactly denotes the function that we are computing for from index id plus 2 or id plus 1. This is the recurrence relation. Now let's go over the C++ implementation using top-down approach. This is the DP table for memoization. We are initializing it with infinity so that we know which state is visited depending on the value present at a particular DP state. If this is infinity, that means it is not visited state, and we need to compute it again. And one more thing, this code is same as problem B, just that we have here we had two jumps available from I to I plus 1 or I plus 2. For that problem, we have the case where it is generalized up to index I plus k, where k is input in that question. So I've used the same code by just hard coding the value for k equals to 2. Next, we take up heights and we start with index id equals to 1, the jumping process, which is the state of the recurrence. So this is the index that we are currently at. If we are at n, that means we have finished the jumping process and we no more need to add any costs. So, and it is the terminating condition. This is to check whether the state is visited. If it is visited, we can simply return the answer from that without computing it again. Next step, this k is equals to 2, which means the values that j can take is either id plus 1 or id plus 2. And if this lies in the permissible range of the indices, then we will consider that choice. And that choice means the index, further jumping process from that index, plus the cost which is required, which is the absolute difference between the heights of those two stones, and return the answer after minimizing it for each state. The time complexity for this is as simple as finding out the unique possible values for the state of the recurrence, which is order n for the only parameter. And since there are only two transitions possible, which is constant, hence the total time complexity would be order n, which is same as the space complexity as well. That's it about this video. If you found this useful or if you have any doubts or suggestions, do let me know in the comments. Thank you.